welcome to Android Developers Backstage. I'm Romain from the Android Toolkit team.
I'm Tor and Romain from the Android Studio and Jetpack teams.
I'm Leland Richardson from the Toolkit team.
And I'm Chuck Jasky from the Compose team.
Yeah, I like that you both use a different name for the team because it's all the same anyway.
Yeah.
All right, so another episode on Compose.
Yeah, awesome.
I can't remember the last time we did an episode on Compose, but there's a lot of things that are constantly happening. And in particular, Chuck and Leland, you've been on the podcast before. You work on the compiler and the runtime, and Leland sometimes other things as well. But there's been a lot of going on, especially around performance and some of the insides of Compose. So yeah, we wanted to just hear from you about what's been happening and what interesting things you've been up to.
Yeah, one of the things we've been working on is a feature called pausable composition, which is going to be, we're trying to get rolling out. What it allows is during prefetch to have composition span frames. So if you have a large item that may take more than a frame to compose, then we can break up the composition between frames.
So when you say prefetch, you mean like, for instance, when I have a scrolling list of elements?
Right, prefetching happens when you scroll a lazy list. And that's essentially what allows us to do is spread out will allow you to stop composition so we can allow the frame to land and then pick up composition after the frame is landed. And then we can do that during prefetch, so it might be actually composing something that won't be on the screen for a couple frames.
So I'm doing some sort of work, and I would then partition that work into like units of work, or is it more
you don't have to do
automated
anything as a developer. So I mean, when you're doing it, it happens pretty much automatically from composition. So when Compose is running composition, at some point we just stop calling your functions, and then we go out of Compose, and then later we pick up by calling your functions again. So,
but if I have a slow function, you're not interrupting or anything.
We're not interrupting the function itself. We're interrupting whenever the function calls something. Then we have control where we can.
So that sounds a lot like coroutines, where when you call a suspend function, that's a place where the coroutine can stop. So I assume we have precedence.
Yeah, it's very similar to coroutines, but it's much more targeted towards Compose, and you don't have to write. It's the Compose compiler the code we generate now is actually sufficient to do this pausing.
So what are the stopping points? Are there calling other composable functions, or do we use
if you call another composable function, basically,
okay.
It's every time you call a composable function, we have an opportunity to stop, and we will skip that function. We'll still complete the outer function, but we will stop going into nested functions, and then once we leave that function, we'll start doing the same thing going back up.
Compiler plugins strike again.
Yeah,
it's nice.
Yeah. So specifically, the way that we're able to skip functions in Compose is kind of what enables this. So ever since Compose existed, you would always write composable functions sort of with the understanding that when something called that function, it's possible that it would get skipped if the inputs were the same. And so that same machinery is basically what we use. And so when we're executing a composable function, if we think that we don't have much time left in the idle window before the next frame, then what we can do is we can start telling the composer to start skipping functions. And so if you think of like the call graph of all of your composables, then we just sort of shallowly finish whatever the graph is instead of traversing deeply.
Yeah, and that would be terrible if it was on the screen, but the point is this is not on the screen. This is you're sort of looking ahead. And
yeah, right. This is during prefetch. So you're building something between the frames that will eventually, we believe, will land in a future frame. If it's required in the frame, we will complete composition. We'll essentially restart it and then complete composition, and then we'll do the layout and draw.
So you mentioned prefetch, but I imagine we could generalize that, and this could be a mechanism we could make available for anything that you want to do asynchronously, right? Where you want to preload content.
Right. Yeah. That's that's a future. Right now,
right.
We're landing it in prefetch. The idea is to have what other places can we do it? The first place is trying to move work out of the frame. So that's pretty much what we're trying to do. Is that you're trying to land a frame, and we're trying to do the minimal amount of work necessary to land the frame and allow people to do work outside the frame. So the first thing is...
I was just going to say, to be clear for the listeners, when you mean out of the frame, we're still talking about the main thread. We're not moving...
Well, yeah, the main thread, it's not moving things out of the thread. When Android asks for a frame, we have to run composition, we have to run layout and draw. That's what the work we do in the frame. What prefetch allows us to do with lazy lists is we can predict when an item is likely to be needed. because you're scrolling operations and things like that. So we try and predict what the operation is. And so we try and prefetch the items that we think are going to be on the screen. We've been doing that since Compose 1.0. What we can do now is the problem is if you do prefetch and the item ends up taking more than 16 milliseconds just to compose, there's nothing we can do. We're going to jank.
And then you had to be more conservative and prefetch less,
right,
I'm assuming.
Yeah. So at that point, we run into something that says, oh, this takes too long to do prefetch, so prefetch becomes disabled, and it has a downstream effect is that the whole thing appears slower. What this allows us to do is that when we run into a large item, we can break up that item across multiple frames. So the fast items will still be fast, but one large item is not going to.
And you could also
prefetch.
Just do a lot more then, because
we could be more aggressive on what we do in prefetch.
And you mentioned 16 milliseconds, but nowadays we have a lot of phones
with
120
milliseconds.
Yeah, it's more likely to be 8, so it's that much more important for us to.
Yeah, but usually if it's 8, we have a higher processor as well. So the focus we have is like on a low processors, we probably have 16 milliseconds, and we focus really on trying to get the performance of the weaker processors down up, because that will benefit the higher ones in any case.
Yeah, we should all be using really slow computers. I don't know.
Have you tried Studio on a slow computer?
I know. Yeah, it would be a good incentive.
It would be a good incentive. But yeah, no, that's a fantastic feature, and the idea that we could make that available more broadly to do like any kind of like preloading that you might control outside of the lazy.
Yeah, the other part. So there's one is anytime you want to move composition outside the frame, then this becomes an applicable thing to do. The other one is it allows you to do that kind of work on the main thread, but split it across multiple frames. So you can think in a navigation scenario would be a reasonable thing where you're going to be navigating to another compose view, and you know that it probably takes more time than just what you can do in a single frame. So it allows you to say, well, I can display an animation or a spinner while it's trying to construct the rest of.
It's interesting because it's a similar technique that's used in rendering engines or games, for instance, where you try to do some of the work ahead of the next frame whenever you have a bubble in your pipeline.
Yes.
And hopefully most of the time it's enough, and things go well.
I think a lot of people are excited about some of the shared element transition APIs that we've created, and I think that this will be able to serve that use case really well, where when you're navigating to a new screen and you want to have some animation that goes across the transition, you basically have to compose a very large piece of content, which is going to often take more than a single frame, but you're doing it right when you're wanting to start a frame.
You're doing both the before and after. You need them both for the animation. Is that why it's more expensive?
Yeah, exactly.
Yeah, you need to know what you're animating to.
Yeah.
Right.
So, yeah.
And so then what this allows us to do is to basically make it so that part of the animation could start before that content's ready, but then start the animation to go to the next screen. And then while something is animating, we're kind of making sure that we don't miss a frame for any of those things rather than doing a bunch of work.
Even if I project myself a little bit, web browsers do something like this where they start loading a page that either because your mouse cursor is getting close to the link or because they think that's the next likely link. So I could imagine an app, knowing that 90% of the time, the user will click next. So they could start pre-composing that next screen, knowing that the user will go there anyway.
That reminds me of, like in the old days, maybe people still do this, but, you would basically, for profiling, you would capture usage data and you would feed that to the profiler. So it knows like which branches are most likely held. And I'm wondering, if you have baseline profiles and things like that you could feed.
Navigation profiles.
Yeah, right? So we could actually have some information about what is a likely succession of composables that the compiler sees. And so you could actually more aggressively do this.
I think one of the things that is not quite that, but I think can get you a lot of the same benefits is, if you work with navigation, what you can kind of think about is you can use the route as sort of something that can group screens by their general shape. And so like, let's say like a typical case might be you have like a master detail type screen. And for the detail screen, you can kind of assume that like the rough shape of the composition is going to be the same for all of those detail screens. And so then the navigation library could essentially take advantage of that. And then we can, kind of do some optimizations in the runtime to basically pre-allocate the slot table and the
I see. So by
address
shape, you
space and
mean
stuff
sort
like
of
that.
size. Of,
Yeah, we do this kind of thing already in the lazy list, and it's basically taking the same concepts that we did for the lazy list and trying to see if there's more places we can use that same technique. So in this case, it's describing reusable content, which is what the lazy list does, and the shape is defined by the category, the type of the item, and we reuse the content based on the same type of item. So if you have like 4 different items, we won't be reusing item, the address item for the image item. So you put those in 2 different buckets, and we will reuse out of those buckets. We can do the same thing for navigation.
That makes sense. I mean, you could even push that like all the way to, any component, right? Like if you have a button on one screen, you have a button on another screen. You could reuse that bit as well, maybe.
Well, that becomes a little harder unless we know. I mean, that becomes harder. Is knowing.
I didn't say
at
it was
that
easy.
granular level. Yeah, at that granular level, it's harder because the information we would need to maintain to figure out that it's the same is probably more expensive than just
Right.
building it from scratch.
Yeah.
So that it becomes a balance. So, and there's certain cases where the item is expensive, and that's where movable content was
Right.
designed to do. Is like when you know that something might be expensive and it's used on multiple screens or it's moving between screens, then you could put it in mobile content, and that movable content will move. So the slot space that we've allocated will move with the content.
Yeah, I hate when that happens, when the optimization is more expensive than just
Yeah,
doing the work.
that's the problem. Is that's what we face a lot of times with runtime, and we come up with these great ideas, and it's like, oh well, that's way too much information to maintain, and we're not actually saving. It's not actually paying for itself. And so there's other things that we've did. Like for example, we had initially we did compose. We're really focused on getting accuracy. Like we were focused on correctness.
it's a good place to start.
Yeah, it's. I mean, I don't regret doing it, but the one thing about that became confusing to people using Compose was when you're using a data type that you never modify, trying to get Compose to generate the code that says, well, I know this is never going to be modified, so I can use it directly. Protobufs are a good example of this. You get something deserialized off the wire, and you want to send it directly to the UI to be rendered. For us, we go, well, we don't know whether it's going to be modified or not. It looks like it has modification APIs, so whatever. And so we would be very conservative about the code we generated, and we would compose a lot. So we added a feature called strong skipping, which says, okay, just treat all objects as if they were stable, which means that we will generate the same code, the same checking code that we do for objects that are immutable, as the same code that we would generate for objects
But
normal objects.
what you're mentioning is interesting, right? Because it's the story of all compilers or JITs or whatever. Like there are things as a developer that the compiler can't know or can't assume or can't prove true.
But I think I'm missing something. So you basically are now getting mutable objects and saying, well, probably they're fine, right?
Yeah,
so,
we assume, like, one of the things we do for correctness is that there's 2 constraints for correctness. One of them is that if anything changes, we need to be notified. And if we call equals, it will return false if the previous state is different from the current state. Mutable objects, that's not true ever, right? Because you have reference semantics. So if you call equals, you have the same object in both the slot table that was there before and the new slot table that's being built. And if you call equals, it'll always be true because it's the same instance. And so even if you changed it, we can't tell that you changed it because we have nothing to compare it against. So mutable objects have never worked well in Compose because of that. So we introduced state objects that said state objects are mutable, but they tell Compose when they've changed. And that's important. But there are a number of objects that people use day to day that they just never modify. They build them, they want to use them in Compose, and they never modify them.
So is it the case now then that we default to assuming things are mutable unless they like implement some interface saying, I am mutable and here's my notification?
Basically, we have there's 2 kind of categories of types that the Compose compiler thinks about, and then that's along the lines of something that we call stable and then unstable, I guess. And so most mutable objects would be considered unstable. And prior to the strong skipping mode, essentially what if you accept it as a parameter, a type that was unstable, it kind of represented a cliff where all of a sudden that composable never skipped. And so now what we've done is we've kind of relaxed the semantics a little bit to where for types that are unstable, we essentially think of instance equality as the thing that's important. And then for types that are stable, we think of structural equality as what's important. And what that does is that kind of, it lessens the cliff a little bit. And what we found was that basically this is how everyone kind of expected Compose to work. And I think that was like a difficult thing for us to come to, because in the very early days of Compose, like we did some user testing and things, and like this kind of specific issue ended up being exactly what people got wrong. And so we were really scared to kind of go down that path, because you get these like...
Just you saying that we're relying on the instance inequality to tell us if something has changed, like, scares the shit out of me.
And so I think that we were, formally it's less correct. It's more, it's less conservative. And I think it took us a while to sort of come to think of this as maybe being okay. And we spent a lot of time kind of trying to understand how people were using Compose in the wild, and if we made this change, what kind of behavior changes it could create.
And you made it, right?
Yeah, and what ended up happening was like basically we made this change, and it basically almost never caused an issue. Like there was some cases in our code where it was a slight issue, and basically every like partner app that we talked to like turn this on basically didn't, it just improved things for them.
So your rollout was like, hey, it's opt-in at first, and then people get much better performance. And is it still opt-in, or is it like, no, this is just how Compose behaves now?
So I think as of Kotlin 2.1, it's on by default.
And that's recent. That's a few weeks ago.
Yeah.
Okay, all right. So this is brand new, hot off the press.
Yeah, and I mean the reception of it has been very positive. People have reported pretty strong performance gains from this.
For free.
But also,
you don't have to do anything.
But I mean, it seems like the more that we like actually look at people's code, it's just like it's creating less confusion, because so many points of confusion were people trying to understand why it didn't work like this.
I'm surprised by this, because I think I would be more confused by the new behavior.
Well, and that was kind of the priors that we held based on some of the early research that we did, was that we thought that, because one of the things that you really don't want to do is like once you have like the types of issues that this can create are the types of issues where people lose faith in like anything working at all. Because it's incredibly frustrating to call a function in your code, like you're writing the code that calls the function, and then the code that calls the function executes, but we don't actually run the function. Like that is an incredibly unsettling bug to run into. And that's why I think we treated this with a lot of care, and it took us a long time to sort of be willing to make this behavioral change, is because we felt like the stakes were so high. But the more we tested it, the more that people, because what we ended up getting instead was that there were people that have like a rough understanding of Compose, and they say, okay, Compose is fast because it's able to skip functions. And so then they like write their code kind of assuming that's going to happen, and then it doesn't happen, and then they're frustrated for that reason.
But hearing you describe all of this, I think you basically did the right thing, because now that folks have a rough understanding of how Compose works and so on, like, yeah, it might make sense. But when we introduced Compose, it was such a departure from the way you were writing Android apps that it probably made a lot of sense to be more conservative.
Yeah, that's one of the reasons why I don't regret what we did, because Compose is successful. So, we obviously didn't do it entirely wrong at the beginning, but the more you learn about, when people were learning about skipping, and once they got it in, an intuitive sense of what skipping did and restarting, the two major optimizations we do in Compose is skipping and restarting. So once you understand what's going to happen, they were looking and saying, okay, why didn't this skip? And our answers were, well, you have an unstable object, and we have a compiler analysis we can do. We can emit a file that tells you when you have an unstable parameter, but it's only if that unstable parameter was modified, or, there's other cases for which, that it did skip, but not with, because you had a default parameter that was unstable, but you didn't use that parameter. And so it started skipping. So it was really difficult to describe to people when it would skip and when it wouldn't. And we couldn't give a complete analysis statically of exactly which times it would and which one it wouldn't. And so this bit is a lot more consistent. It's like if the object returns equals true, then we assume that it didn't change.
I wonder if you could have some sort of a debug mode where you just do extra state checking and you basically flag when this was the case.
Well, right now, if you set a breakpoint in a composable function, the variables watch window will actually tell you like the state of each of your parameters to that composable function, and it'll explain which parameters kind of cause that function to run that time. So like there are some.
It doesn't tell you when it didn't run. I mean, because obviously the breakpoint wouldn't hit.
Yeah, although you can set a breakpoint at the top line of the function, right, yeah, and it'll.
I just meant that if we had some kind of a checking, right, where we call these functions more than we should, and if we see that some fields change but not equals, we go like, this is suspicious.
Yeah, the problem is that,
again, not for real production.
Yeah, I understand.
I'm talking about
I understand
like
what you're getting at, because I worked on frameworks that have similar features, and one of the things that we found is that that's actually a really confusing thing to do, because in debug mode we're calling it more often, so you get this. It's not doing what it's going to do at runtime.
Yeah. I didn't mean every time you run, because debug mode was a bad term. I don't mean when you're developing.
Mode
exactly, diagnostics mode. Like, hey, look for jank, look for
right.
Look for.
The problem is trying to come up with a model that says this is definitely wrong.
Yeah.
Because
you're gonna have false
probably
positives
doesn't know.
Sure.
What, I mean, it didn't change, but I didn't know whether it was supposed to change or not because I don't have any mathematical model to say this is correct. If we would have done extra work, we would have figured that out. We're defining what it means to be equal, and at that point, you've already changed the definition.
Yeah, because what you mentioned, like if you look at this field has changed but equals returns true. Well, maybe that was the intention of that object.
Yeah,
like you don't have to test every field in an equality test. Like so.
Yeah. So I don't know what the problem is. False positives or false negatives in this case, where it says. This might be wrong, but I don't know if it is or not. That's a really bad diagnostic to give someone.
Although it can be funny to watch developers, spend time trying to fix something.
It leads to, I think, aberrant behavior, which is that they will code around the diagnostic because they don't know whether it's right either, and so they'll write their code to avoid the diagnostic when it wasn't actually.
I mean, that's always the problem whenever because we've had endless discussions, whether for Compose or for Views, about could we look at what's going on and tell you what you're doing wrong in your app, right? And even when we try to give guidelines, the problem is that when it comes to performance, it always comes with a but or an if, right? If we tell you, hey, maybe don't always use relative layout. Some folks will hear never use it. It's like, no, that's not what we. But it can be very difficult because sometimes it's very subtle or it doesn't matter in that use case, and it's very hard to explain that, especially through tools.
But not overriding equals is probably a smell. Right.
From my perspective, there's two kinds of types, right? There are value types and there are reference types. For a value type, you want to override equals. From a reference type, you never do it. And so you need to know what type it is. So it's a smell if you're trying to do a value type, but you didn't override equals and you didn't override the hash code. But not all classes are value types. Or in our case, there's a lot of things that are reference types, but you treat them as if they're value types. So, for example, like I was saying, protobufs is a good example, is that you get a result from protobuf. It feels like a value to you, but it's a reference type because of the way it's implemented. And you're allowed to mutate it, but you never do. Right. And so in those cases, there's a certain class of objects where you, as a developer, you don't have control over it. Yeah. You get this from either a library or your back-end development team or somebody else has written this library, and they hand it to you, and now they want you to render it. And before we said, well, you could copy it into an object that Compose understands, but that's a performance problem. Yeah. What strong skipping allows you to do is just say, well, as long as you never modify it, just go ahead and use it.
I mean, a lot of times people play around with a mutable sort of state management where they end up having, something that is mutating at the root, but it's basically producing an immutable kind of tree of data. And sometimes in those cases, you don't actually want to override equals because the actual equals implementation would end up checking like a very large number of fields and be quite expensive. And you're actually assuming that, equals returning false in some cases might be okay as long as that when it returns true, it's accurate. And so then using instance equality as like a very fast equality mechanism for some of those things.
And it's an important point, and it goes back to what you were saying earlier, Chuck, right? When the optimization is more expensive than doing the work, and equals is one of those cases where, I mean, if you imagine you have a hash map made of list of whatever, like doing a true equal, you have to go check everything that's held by this data structure to decide that you're not going to do the work, but you've already done so much work that.
Well, and like, so list, like for instance, like Kotlin, implements content equals for the equals of the list interface. And so this is like kind of dangerous actually. And, one of the most common requests is like for us to think of the list interface as stable. It's not, it's read only, which is different than immutable. But also like there are a lot of cases where that might be a bad thing because there are some pretty big lists out there, and calling equals means that we have to structurally compare every single item in that list. And that can be sometimes more expensive than the composable function that
we probably won't ever use the items that are not, like, I mean, you have passed the list in and you're using a lazy list to display 10 items, and it might have 1,000 items in it, and we don't want to have to compare 1,000 items per frame.
Yeah, especially because like usually the very next function that you're calling is going to then iterate through that list and then pass each item into some other composable function. Right. And so then you end up comparing every item, and then if one of them's not equal, then you dive down one more function, and then you end up comparing every item again, and you end up with this.
I think you have a really strong argument, and so we can just close that request.
Well,
and trying to get to the bottom of the bug.
I think like going back to what Romain was saying is like there ends up being some difficult things to communicate, and then people end up sort of cargo culting certain things as like always being bad.
And to be clear, we're not putting the blame on anyone here. It's just the nature of.
Yeah.
But like with stability, like I think a lot of people early on that were pretty interested in like really understanding how Compose works and stuff. They catch wind of stability as this thing, and then they try and understand the rules, and then they do, and so where it ends up with is like you end up with people that have a pretty good understanding of how the system works, but then they start over applying these sort of like rules of thumb where, then they say, okay, everything has to be stable. And they start worrying a lot about, marking different types as stable. And it was never what we wanted that to be. We always kind of wanted stability to be something that like people didn't have to think that much about.
Well, and it's not just that, because it also becomes your focus. And I've seen that happen, right? Where someone will focus really hard on avoiding a recomposition, and they miss out the fact that when they do recompose, maybe they're doing something horrible with the canvas or graphics layers, or so you have to be careful, right? When you start obsessing about one particular aspect of performance or correctness, you may miss out on other things that are just as important, if not more.
Yeah, and it's like it is something that can cause performance issues, right? Like if you're, something is recomposing, very frequently or something like that. But I think a lot of times it's not the performance issue, and there are other.
Because some composables will be super cheap, and it's not an issue to run them.
Yeah, or it's just not actually running that often, right? I mean, like if you're scrolling through a list and there's like a lot of times for like scrolling performance. The challenge is really the speed of initial composition. So like when you have a lazy column or something, and then you're composing new items as they come into the window, and if you're doing that during a frame like that's where the jank comes from. And so then you can play with stable all day. You're not going to change anything because it's an initial composition. So you have to.
Yeah, I think that's an important point. I mean, it's certainly the thing that I've learned working on the runtime is that performance is really initial composition. It's creating new content, not updating existing content. And when you're talking about recomposition counts, you're talking about updating existing content, not creating new content. And so the performance you lost in recomposition is maybe not where the jank is coming from. It's probably in something that's in the new contents coming on screen.
The only caveat I would add is like updating can be an issue, but it's when it's catastrophic,
this
it's the whole
like
screen or
thing where you're talking about. It's like, it's generally new content, but sometimes it might actually be updating.
Like you're recreating the web view every time,
Oh yeah, something like that. Like if you're doing too much, you're doing too much, and trying to figure out what it is. But generally, what we found in our benchmarks and looking at it is we focus a lot on what does it take to create new content, and how much
Let's
time.
talk about that, because as I understand it, the strong skipping is for updates, right? So what are you doing about this problem? Strong skipping is already shipping and stable, and the prefetching is in what state?
Well, prefetching is already there. The possible composition is sort of an experimental state where it's in the runtime, but nothing above the runtime takes advantage of it yet.
Okay, all right. There's
a lot of focus right now on improving the way prefetch works, and possible composition is like a big part of that. There's other improvements.
Can you explain
things.
what we found about prefetching? Won't we prefetching something and dropping it right away or something?
There's a few issues with prefetch. I mean, like one of the right now, our prefetch strategy is fairly primitive. So like the way it works is we basically we allow for a single item in your list to get prefetched that's like outside of the visible window. And then that's basically it. So you have like the visible viewport of the list, and then in the direction of scroll, we prefetch like one.
So
one
per
additional
frame,
item.
I can only get at most one prefetch. So if I scroll really fast,
Yeah, I mean, usually, so the height of the items matters. So if you have relatively short items, and then like a reasonably fast fling, then you're probably going to be pulling in more than one item per frame for at least part of that fling. So that's definitely like one aspect here. The other thing is like you can end up with, if you have like a heterogeneous list where there's different item types, sometimes like a common pattern we see is like people use an item for like a divider or something that's like two pixels high or something like that. And so then what happens is that like that one divider ends up occupying the single item that we've prefetched, but it's like basically useless because like anytime you go beyond here. But like part of the problem is that a lot of applications that have sort of leveraged, like they've baked in some assumptions around prefetch that are difficult like for us to go through. So like we're trying to figure out how we can sort of safely change the default strategy for lazy column. But like if you want to like opt into new behavior, like we can, kind of get rid of this. But one of the things that we found was that there's a prefetch strategy API that we added that allows people to kind of implement custom prefetch strategies. So one of the things that we saw people trying to do was have the prefetch window kind of extend in both directions. So if someone's scrolling and you're prefetching in the direction of scroll, that's great. But then if you change directions, like what happens then? And so people are trying to prefetch items in both directions. And then what you end up seeing happen is that as an item leaves the visual viewport, we dispose it, and then we immediately prefetch it. So there's like a bunch of sort of extra work.
Like a post-fetch.
Yeah. So one of the things that we're doing right now is kind of trying to reevaluate what the sort of the optimal prefetch strategy should be. Some of that is in light of the pausable composition work that we're doing. We're trying to make it so that people can prefetch more than a single item for longer distances outside of the visual viewport, and also like just be a little bit smarter about the scheduling. Like one of the things that we found is we're running into situations where there's actually kind of quite a bit of idle time that we could do prefetch, but we're not, and we're trying to understand like what calculations are causing that to not happen.
Yeah, possible composition gives us more freedom of what to do with the scheduling, but the scheduling is very important about trying to figure out how we take advantage of the idle space between frames and how to effectively move work out of the frame and into the space between the frames.
Well, and hopefully we do have idle time between frames.
Well, there are cases when we run out of time. Like
right.
You have a large item and we have.
But usually when you scroll a list, because we do have optimizations where most of the items are just being translated, so those tend to be cheap frames.
Most frames are you're just moving a layer or a few layers, and it's not that expensive.
Yeah, when you talk about like if you go to 6 or 8 milliseconds, the wall clock hasn't changed. So the speed of which the fling is happening hasn't really changed. So it means that fewer items are actually being created per frame in that case. So even if we have faster rate, we have to do have to do a lot less work. We have a lot less time to do work, but we end up doing sometimes half the work that we would do in 16 milliseconds.
And one of the things that I've been looking at lately is, sometimes you get into a state where there's actually like a bit of back pressure with Surface Flinger to where we're delivering a frame before the previous frame is ready from the runner thread. And so then what ends up happening there is there's some number of milliseconds on the main thread where we're basically just waiting for the render thread of the previous frame to finish. And that situation, when you get into that sort of scheduling
when you get ahead
problem,
of the GPU.
Right. So what that can do is like really kill prefetch, because then the current way that we schedule like idle time, because there's like a decent amount of time that we've spent waiting, it's like that time plus the time that we would normally spend on the main thread. And so then what we have left is maybe just, a millisecond or two. And so one of the things that I'm looking at is basically doing some tracking to better understand when we're in that situation, and basically adjusting the scheduling so that prefetch actually feels comfortable going over the next frame's start time, and actually potentially improving the scheduling situation, because then we're kind of giving the render thread room to catch up.
So did I understand correctly that the issue is that you're way ahead of the schedule, you're about to hit a frame boundary, but the prefetch thing is like, oh, we're running out of time, because it doesn't know that it's a frame ahead. And that's why. And so what you just need to teach it, like, no, this is okay. This is you're a day early. Keep going. Is that basically?
Yeah, I mean, more or less. And it is kind of difficult to detect this situation from the main thread, but I'm pretty confident that we can insert some measurements at the right time to be able to understand when we're in this situation, and then basically give the prefetcher more room.
But it's interesting you mentioned that, because that shows, that's the point I was making earlier, where it can still be important, not in all cases, to optimize also your layout and your rendering, so that we don't give too much work to the GPU. Because, we can go to triple buffered, but there's a limit to, there's 3 buffers. So when the queue is stuffed, we have to wait.
Well, I think normally what happens is this is a case where there was one frame that was really expensive. And so then because of that, like Surface Flinger kicks into like a triple buffering mode. And then there's not really an opportunity for us to like let Surface Flinger catch back up until the scroll's over. And so there might be like an expensive frame early on that sort of kicks us into this state, and then it's hard to get out of it. But during that time, you've kind of ruined the potential for like prefetch to do a good job.
Yeah, we can obviously like mitigate that problem, but my point is that you can also help in the app itself by being careful. So, if you're doing a lot of custom drawing, or using a ton of graphics layers or whatever, like you can optimize that to avoid getting in that situation in the first place.
Yeah.
Yeah, but you're talking about the Compose. I mean, I'm Compose compiler in
Right, no, absolutely.
So that's above me. Somebody above me can.
Sure, but it's all intertwined. Like the point that we can help and mitigate problems, but we can't solve everything.
Right.
It's like when I talk about optimizations or even macro optimizations, and someone will tell me like, "Oh, the compiler will figure it out." I'm like, well, it can't always. Like I would love that, but
Yeah.
it's.
Yeah, it can't. There are certain things it can't do. It can't figure out when it could not do something because you told it to do it, but it might not be required. But it can't figure out that you didn't need that. And that's kind of the situation we're getting into, is trying to figure out, well, maybe we can give it a little bit more time to catch up. There are certain cases where we can do that from a scheduling perspective.
And again, ultimately, our goal is that, of course, out of the box, without thinking about it too much, we want you to have amazing performance with Compose, but we also want to get to a state where if you do run into performance issues, we can at least confidently say, hey, it's not the runtime. We've done everything we can. I don't know if or when we're ever going to get to that state, but
I still want a job.
Signed right
there. So I'll still come up with things that we can.
Oh, I'm sure you won't run out of ideas.
Yeah, but there is like the crossover point where the bigger bang for the buck. We had early in Compose, we had a lot of headroom we could do for changes to the runtime and the compiler, and we've done a lot of those. Now we're being more creative and trying to deliver the performance. Going back to one of the questions you had about what are we doing about rate performance, and part of that is going back, and for me it's going back and figuring out what is Compose actually, what's the mathematical model that Compose is using to describe its behavior, and what can I do in thinking about it that way that allows me to remove work one of those things was a rethinking about how information is stored within the slot table, which is where we store the information between composition. We store what the composition did so that we have enough information to figure out when the new composition comes, what changed. Okay, so that's what the slot table does. It turns out that we went through a process of trying to see if we can get rid of some of what we call groups, which track this information. And we ended up coming up with a different way of thinking about compose. Instead of thinking about it as I'm tracking all the calls you're making, to I'm actually tracking the changes in flow of the application. And that allowed us to get rid of a lot of groups that would just be the same groups generated even if the code didn't change. And so it allowed us to reduce the amount of overhead that we generate during initial composition. So we generate less data to track the same state. And so there's things like that we're trying to look at. Is there other places we can do the same opportunity? And anytime we can reduce the size of the amount of information we collect, that has a pretty well correlated effect on the performance. It's not always 1-to-1, but it's pretty strong. And we've done a lot of trying to remove the things that are just redundant information that we didn't need to record. And we call that group alighting. So if you see that as a flag inside of the compiler, that's what it's talking about, is reducing the number of groups that we have to track. And that required some changes in the runtime that are detailed that I want to go into. But it means that there are certain things that that could happen in the runtime that didn't happen before.
Yeah. And I think that's important for you to mention that, because I know a lot of people know, I mean, there's a compiler plugin, but it's hard. It's kind of like with coroutines, right? Until you look at the generated code, you don't realize that what you write is absolutely not what gets executed. And
yeah,
of course, ideally, we would generate like nothing.
We're trying to deliver the mental model that composition is a transform function that transforms the data you have in your application to a user interface. When the data changes, the interface changes. And so we will reevaluate the transform every time we detect the data has changed. And the idea is that if we ran that same transform completely, like we ignored all the skipping and restarting, you should get the same result. There are different ways to do that.
I like how non-confident you are when you say that.
Yeah, well, the thing is, I know all the cases. Well, I know all the cases that don't work. So whenever I say things like that, my mind is coming up with all the counterexamples where yes, but Chuck, what about this? And so when I say that we try to do that, is because we try very hard to do it and we get really, really close. But there are things like mutable types which we can't do anything about. They're reading a global variable which might be changing, which we didn't get told about. Things like that. And that's where things fall down, is when things are not obeying the mental model that Compose was built with, which is that, like I said, when Compose needs to be notified when anything changes, so that it knows when to rerun the functions, which means that Compose also needs to record what data you read, so it knows how to correlate, this data you read in this function, so therefore when that data changes, this function needs to be re-executed. And so there's a lot of information that we track. And if that doesn't get recorded correctly, then you'll get a difference between that mental model of the transform function. If I started it from scratch, will generate a different result.
I'm wondering if we were to expose some more of this information in the code editor. So the user, like, let's say before strong skipping, right? If stable and unstable had different.
Did we talk about cargo culting earlier?
The one thing we want to give is a lot of feedback about. Whenever you give feedback like that, what you're saying is this is a very important thing that you need to think about. That understanding this is very important to the performance of your application. But that, in a lot of cases, is not true. And so giving that information is sort of like people. What I want to avoid is people or developers getting feedback in the IDE, telling them that there's a problem. When that
I didn't mean warning. Like, for example, like in Studio, if fields and variables have a different color, right? And it's like useful to you to understand, like, this is the field I'm manipulating. I'm just wondering if there was something where I want to see that I'm binding this field to a UI element. Would it be useful?
Actually, in general, what I would love to have is just Lambda to know what I'm binding that's outside the Lambda. It's not related to compose.
Yeah, I mean, some things that we've talked about are like really trying to understand in the editor where state reads are taking place, and I think that would be valuable. Like if you, if you're looking at a composable function in code, you might be able to like very easily at a glance see when there's a mutable state or something that you remembered in the function, and then down here you read it. Like that you can kind of see, but a lot of times those reads are hidden from you, and so there might be some function that you call which calls another function which calls another function which then does a state read, and so then that read is kind of hidden from you, and so like being able to kind of understand
like somewhere other than in this function.
Yeah, so it's in the call graph of the function, but it's not in the text of the function body.
I mean, if this is statically determinable, like one thing that I like that the IDE does, like if you put the caret like on the return type, it'll highlight all the exit points from the method, for example, right?
Yeah.
So I'm wondering, like, if the caret was on a remember, could we determine statically like the call sites that should be highlighted as like the
for state
is,
reads? No.
Because state reads are transitive, and that means they can cross module boundaries, which means that we don't have enough information at the call site to determine.
Okay.
It requires global analysis of the application,
Okay. All right.
which might actually not be applicable when you're writing code, because which application are you talking about of all the different ways you generate an APK? Which one are we talking about?
A good example is what we do ourselves when we write compose to a library, right?
Yeah.
It ends up in an app, and we.
Well, any virtual call, you won't be able to prove
you can't
that doesn't
determine
have
what
a
the
state
virtuals
read
are.
in it.
Math, it's like one of those things. It's like, well, that sounds great, but the math doesn't work.
Well, you might be able to catch like a lot of them, but it would. There's some problems with tools that catch 90% of the state reads, but not 100%, and then you give some false confidence, like, oh, okay, this thing isn't reading. I don't know.
Yeah,
so
I mean, IntelliJ has this feature where they highlight unused calls.
Mm-hmm.
And basically the way that works, because they can't do global analysis, right? But they have an index. And so if they see that if there's a method declaration and that method name is not read anywhere, it'll be highlighted as this is unused. But if you have a field name somewhere else with the same, like, well, now there's a clash in the name map, in the name table. So it goes like, okay, so you'll often have false positives on unused, but it's kind of cool when it happens. You write a global function and it goes, oh, it's unused. Oh, interesting, right? And
so like as soon as you have like the invocation of a parameterless lambda, it's like, shoot.
Yeah.
There's going to be a whole lot of lambdas in your application that read a state, and so it is like I think it could be useful as a tool if it's like understood that this is just an aid and it's not like a proof of where all the state reads are.
But it goes back to what I was saying earlier, where it can become very difficult for us to explain, especially in the context of a tool, what are the limits of that tool, and how it's supposed to be used, and where it helps you or where it doesn't. And so just being able to build a tool is unfortunately not quite enough.
Well, and then also it's like I can imagine something like that being like somehow taken to the extreme of like, okay, let's avoid all state reads in composition. And that I think that's already like a perception that I sort of try and combat. I think that there are like types of state reads that you do want to avoid, where like if you have some state object that is frequently changing, then reading that in composition, if it is something that could be read, say, only in draw or only in layout, then like that makes sense. That's a good trade-off to restructure your code such that it is only read in draw. But if it's something that is almost never changing, then a lot of times actually moving the state read into draw might be more expensive on average than actually just reading it in composition, because now you have to allocate a lambda in order to pass it into like a draw modifier or something like that. And then now we're causing the draw phase to be slightly more expensive, because now the draw phase, which gets executed much more frequently, it involves a state read and a lambda invocation or like all these things that it wouldn't have otherwise. And so these trade-offs are like non-trivial, but like what I see a lot of people take away is all state reads should be out of composition. And that's just not true. But a lot of times the problems that people run into are overreading state and composition, and so it's just like a challenging thing to.
You can't have a hard and fast rule, basically.
No, there's just one rule with performance: it depends.
Yeah, you need to trace.
Yes. Yeah. But yeah, that's another great example of it can be useful to have tools, but it can be misleading or make you obsess about.
There are some things we can do with. I mean, you talk about the compiler, but there's also the runtime. There's some things that we can do in the runtime which we've worked on. One part of that was like we have the tracing API that allows you to get tracing information that's a little bit lighter, more targeted to compose. You can enable that. We're working on ways to make diagnostics in the runtime better. We're working on, for example, we're just landing a change that correlates when an exception happens in your code. It correlates what part of composition actually generated the thing that's causing the exception. So, for example, if you have a modifier that's doing a callback and it generates an exception, well, where was that modifier created and where did it enter composition? And we use the slot table, which contains a lot of this information, to try and extract out of it where in the code that generated
Which is good because since you're throwing an exception, it's already a very expensive operation.
Right.
So you might as well do extra work because I know that exceptions and the stack traces that Compose can generate can be intimidating and not always exactly helpful.
Well, one of the problems you have with stack traces now is that your code's never in it.
Yeah.
So something happened because it's some callback, like apply changes is happening, and you caused the apply changes to happen, but your code's not executing. But it was your fault. We just say, well, it happened somewhere in Compose. Good luck. What this allows us to do in those cases is correlate that back to the code that actually created the issue.
It reminds me, years ago, I think I told that story on the podcast before, but we added an exception in list view that goes out of its way. It has a couple paragraphs of explanations because it's an exception that happens when effectively you're modifying your data adapter from the wrong thread. And when the crashes would happen, they would be deep inside the list view code. And so we would be bombarded.
So this was self-defense.
Yeah, because we would keep getting bug reports. And every time I would reassign the bug reports back to the apps internally. And they'd be like, no, look, the stack trace, my code is not there. I'm like, yeah, but that's still your fault.
Yeah.
So
that's the problem with the current stack traces for Compose. We get a lot of those right now for Compose because it's like my code's not in here.
And that makes sense. I completely understand why developers don't know.
Yeah, I think this is maybe an underappreciated part of API design. Maybe it's not even API design, right? But the API of your error throwing, making sure those error messages are good and actionable, and like that is a really, really valuable thing for people.
It's culprit detection, right? It's like who is the culprit for this exception, and how easy is that to detect?
It's just so easy to focus on the happy path, right? But realize that many developers will have some unhappy paths on the way to the happy path, right? And making that part of the experience better is really, really useful.
Yeah, there's also things that we can use with the information in the slot table, like some of the things that you were talking about of tracking what data is read in a composable function. We can't do that at compile time, but we have it at runtime because we need it, right? So the slot table stores it. The question is, how do we get that in a presentable fashion, saying, oh, by the way, this when you're looking at this function, all these data items were read. And then we need to figure out, okay, well, if it was read, all we have is the instance. Where is that instance created? How do you track that back to the code that created the instance that was being read? And so there's things that we're working about that, trying to track that information so that we can correlate the change you're making in your data to what recomposition is it causing.
And of course, you want to track that data in a way that's efficient.
Right. Yeah. In this case, when you have that enabled, we can be a little less efficient.
Right. If it's an opt-in, yeah.
Yeah. So that's an opt-in. We don't do that all the time. We do track the information, but we don't track it in a way that's convenient to extract because that would take time, and I don't want to take any time.
In general, I've done that in the past. I kind of because sometimes, it's not practical to do this kind of checking or tracking constantly because it comes at a cost when you're a framework. But if you can make it an opt-in so that as a developer, I have a crash and maybe the error tells me like, hey, turn that on. You turn it on.
Right. That's the idea, is that you have a repro case that crashes and it says, okay, well, let's turn this diagnostic on to see if I can get more information about why it's crashing. That's the kind of scenario that we're going into, is like you want to turn this diagnostic information on, or you have a performance problem and you say, well, what's actually happening? And so you go through the scenario that has a performance problem, and then you see how many state reads are doing and how much the change is happening.
So I know some people, like, they have their debug builds with Leak Canary on. But it sounds from our earlier discussion like you'd be a little reluctant to have like debug builds and production builds be different. Like, is this the kind of thing we could have on in debug builds, or like no?
In this case, it's actually too much information.
Okay.
We're collecting source information that we normally wouldn't collect.
Okay.
that we only collect now for layout inspector, for example. So if you're in the layout inspector and you turn that on, we'll collect a lot of data, a lot of source information that we don't need during runtime.
It reminds me, in native code when you have things like, what used to be valgrind, but asan or tsan, like the kind of things that will check for memory leaks, or if you're doing the wrong threading, those are very expensive.
This is the kind of thing we're talking about. Like it's what the old heap checkers would do by just like, I'm going to put your heap allocation at the end of a page, so if you go beyond it, it'll give you an exception. It slows down your application, but you immediately get exception in the right place. And we're talking about these kind of diagnostic modes, which are much more expensive to do if we're doing them all the time, but are invaluable for
when you have.
And back to your point, like a debug app on Android, the name is almost like, I never like that name because it's not really debug. It's really that you
development.
It's not release, right? It's you're not signing the APK. And that doesn't mean you want to go super slow. It's because most of the time you're just testing your code, you're just playing with the app. You're not trying to.
One of the problems that people have is they do evaluate the performance of the application when they run the debugger.
Yeah, they really shouldn't do that.
Well, no, but it's you want that feel to be, and the point that Romain is getting, the feedback he's given us to as the runtime team is that this is an important scenario, is that the performance feedback you get during debug time should be good, so you don't think, oh, well, Compose is really slow all the time.
Yeah, I just think we're dealing with like two types of user, because the other user's like, I don't know what I'm doing. What does this crash mean? Right? Yeah. And it's more helpful to point them to like, here's your problem. You got to add internet permission in your manifest.
Right, but that's where you find a compromise, right? Where we can tell you, hey, there's a
if only
deeper debug mode.
The Android Studio team.
Yes. I think we could go another 2 hours.
Yes.
But
yeah, we need to eat.
I'm sure we'll have you back on again. But it's a lot of exciting stuff happening.
All right. Yeah, thank you.
Yeah, it was fun.